Okay, so how can I use parts of a polygon to find the area? Well, we know the area formula. The area of a regular polygon equals 1/2 times the apothem times the perimeter. So, well, what if we don't know the apothem? What can we do? Well, we can solve for it. We can use our background in trigonometry and figure out what the apothem equals using what information we do have. So here's an example. We are given a regular hexagon, so 6 sides, and we know that the perimeter is 30 inches. So if we take those 30 inches and evenly divide them up among our regular congruent sides here, we know that we have 5 inches per side. Alright, the next step is to determine what is the apothem. Well, we need to label it. So from the center of our hexagon, going down as a perpendicular bisector to one of our sides, we label our apothem. Okay? And this hexagon's been divided up into some triangles. I pulled out the triangle that we see here into a separate diagram so we can kind of analyze it a little bit better. So that's the one that we're seeing right here. Is this triangle. There we go. Now, since it's a hexagon and there's all of these central angles coming together at this point, if we went all the way around all of our central angles, that would be 360 degrees, right? So 6 angles cutting up 360 degrees gives us 60 degrees per angle. So that's what we get for the central angle here. Okay, our next step is we went next door and said, well, if I know a little bit about that triangle, what else can I do with it? Well, that perpendicular bisector gave us a beautiful right triangle that we can deal with, so I pulled that right triangle out of this triangle. So here's our apothem, still on the left. Our angle up top is now 30 degrees because this bisected it, cutting it directly in half. And then the same thing happened with our side down here. The whole side was 5, so half of that gives us a measure of 2.5. Now we can solve for the unknown. We can go to using trig, or we can use our knowledge about special right triangles. If you have your notebook in front of you on page 8, we made some notes about special right triangles. So this one happens to be a 30, 60, 90 triangle, and the short side is 2.5. See how that corresponds there. Short side, short side. So then our long side is A. And to find the measure of the long side, all we do is take the short side and multiply it by rad 3. So here's that computation. We did A equals 2.5 times rad 3. And I just converted that into 5 rad 3 over 2, because 2.5 is the same as 5 halves, just to make it a little bit more pretty. Okay, so we write that measurement over here for our A value. Now we have all we need to solve for area. We have our perimeter and our apothem. So we plug in our values. 1/2 times 5 rad 3 over 2 times 30. And since I was dealing with fractions, I just made everything a fraction, stuck a 1 underneath 30. Multiply straight across all the numerator values gives us 150 rad 3. And everything in our denominator gives us a product of 4. Last step in writing our final answer is to simplify. So I divided the numerator and the denominator both by 2 just to reduce it. So divide that by 2, both on the top and on the bottom. Okay, so we get 75 rad 3 over 2 square inches. Alright, moving on to our next example. Now we've got a regular pentagon, so 5 sides again. And we know also our given information tells us that each side is 7 inches. So let's find the perimeter. Since there's 5 sides, 7 times 5 is 35. Now we need our central angle. Again, all the way around, all the central angles will be 360 degrees. So we take that, divide it by the number of angles, which happens to also be the number of sides, 5, and we get 72 degrees. So that is our central angle. That's also the same value in this triangle that I pulled out. So that's the same triangle. Base of 7, altitude is going to be our apothem. Alright, and then we can go ahead and use that same technique that we used earlier. Just look at the right triangle piece in order to solve for what we need to figure out. So I pulled out the right triangle, leaving us with one leg that's A, another leg that's 3.5. And in relation to our angle 36 degrees, we get that from right here. 72 divided by 2 is 36. A is our adjacent side, so I labeled it A for adjacent, which I didn't really need to. There's already an A there. And then 3.5 is our opposite side. It's directly opposite of angle 36. So if we're dealing with opposite and adjacent, well, we can use tangent. So we do the tangent of 36 degrees equals opposite over adjacent, 3.5 over A. Using cross products, we can take and solve it like a proportion. So A times tangent of 36 will equal 3.5. In order to isolate our variable, we divide both sides by the tangent of 36 degrees, giving us approximately 4.817. There's our apothem. So we wrote that down off to the side. We have both important pieces of information now, and we can put them right into our equation. The area is equal to 0.5 times our apothem times our perimeter. And there's our solution. Okay, I think you're starting to get this. Let's look at another example though. More examples, the better. Alright, so here we have a decagon, so 10 sides, and we're also given that one of the sides equals 8. So all the sides equal 8 each. And then if we have the sum of all the sides, we'll get our perimeter, 10 sides. That gives us a sum total of 80 inches all the way around for the perimeter. Okay, so we got perimeter, 80. Next, we're going to discover what our apothem is. Well, there it is already, but spoiler alert. Okay, we have to go back and do the math. Alright, so central angle, 360 degrees all the way around. Divide it by the number of sides, 10. And we get 36 degrees per central angle. Okay, and then we drew in our apothem down below and pulled out that triangle to investigate. So here's that 8-inch side. Well, here it is again. I just kind of magnified it a little bit so we could see the picture bigger and better. And then from there we pulled out a right triangle and related it directly from what we were given. So if the whole thing down here was 8, then we have 4 for half of it. A is going to be our adjacent side next to our angle 18 degrees. Because, you know, 18, that's half of 36. Our angle was bisected right here. Alright, and now we have another good setup for tangent because we're looking at 18 degrees and opposite of it is 4 and adjacent to it is A. So let's use those values and solve for A. So the tangent of 18 degrees equals 4 over A. I stuck a 1 underneath it, so I'd have a ratio equal to another ratio, and I can do my cross products to solve that proportion. I went over here next. A times tangent of 18 is A times tangent of 18, and that set that equal to 1 times 4, which was 4. The next step happened right here where you see the line. That means divided by, and here's divided by. So both sides were divided by the tangent of 18 in order to isolate our variable A. So those will cancel out, leaving us with A being equal to this value right here. Plug it in the calculator and we get approximately 12.311. And now we have our perimeter and apothem. Plug those in, and the area is equal to 1/2 times, here's our apothem, and here's our perimeter. So there's our final answer, 492.44 square inches. Alright, last example, and then you're going to be brilliant at this. So now we're given an equilateral triangle. All sides are equal, all angles are equal. And in addition, we're given that the sides are each 10 centimeters, okay? So step 1, find the perimeter. Well, 3 sides, each are 10. 10 times 3 is 30. There's our perimeter. Next, find the central angle. 360 degrees if you go all the way around all the central angles. Divide that by the 3 angles, and we get 120 degrees per central angle. There's that. So if this one's 120 degrees, this one's also 120 degrees. They are all congruent. Alright, I pulled out that triangle that's inscribed within the other triangle and placed it here. So here we can see our base of 10 going all the way across. And then I examined just the right triangle that is part of that one, giving us a new base of just 5 when we looked at half of it. A stands for our apothem right there. Since we had 120 degrees all the way across here, our bisected angle gives us half of that, which is 60 degrees here. And now we have another 30, 60, 90 triangle, so another special right triangle. So again, you can look back on page 8 in your notebook if you have that with you, and we can solve for our apothem in a little bit simpler form instead of doing like tangent of a ratio. Okay, so here's our short side, remember? And then our long side equals the short side times rad 3. Well, this time we know the long side, so working backwards, instead of timesing it by rad 3, we have to divide by rad 3. So 5 divided by rad 3 can also be written like this. And then we'd like to rationalize our denominator instead of leaving radicals down there. So we can get rid of the radical and rationalize it by multiplying both the denominator and the numerator by rad 3. When we do that, our numerator is just 5 rad 3. But the square root of 3 times the square root of 3, well, that's the square root of 9, which gives us the 3 that we're left with here. So that is a better way of writing our answer there, rationalized. Okay, so now we have apothem and perimeter. Take both those values, plug them in, you got it. So here's our area formula. Area equals 1/2 times the apothem times the perimeter. So there's all of that. So we have area equals, ooh, that's a funny A, it's moving around. That's not working very well. Silly A. Go back to where you came from. Okay, that's better. Kind of, sort of, a little bit. Alright, so you multiply all those together, and for your numerator, 1 times 5 rad 3 times 30 gives us 150 rad 3. Multiply all your denominators, 2 times 3 times 1, that's just 6. And then to simplify, well actually 6 goes into 150 evenly, giving us just 25 rad 3 left. So there's our area. Thank you.